Alright, back for part 2 of this response video. I guess we'll play the whole video just so there's no accusation that I missed some key phrase. I guess I'll point out just what he's arguing in the end. Okay, so I did watch the second half, pre-watch it. Well, listen to it actually. And in the end, he's arguing that springs collect kinetic energy, not momentum. And he does it based on kind of specious arguments that somehow the momentum doesn't change when the carts hit a spring, when you can physically watch the momentum change. And so that just has to do with his sampling rate. He's taking average velocities apparently. He's not taking the specific velocity at the specific impact time versus the non-impact time. So again, we're doing this experiment, and again, I argued that why do it this way? Why do a 1 to 2 when if you do a 1 to 3, you can get 150 free momentums this way and 50 back this way. And if you do it even 1 to 4, you can get 200 perhaps this way and 100 back this way. A full bounce, as if the object didn't move at all. Now, my intuition, I mean, I'll concede that it's just intuition, is that when I throw a ball against the surface, if the surface doesn't yield, the ball comes back with what I put in. If the surface yields, I'm obviously losing reflection, so the energy's staying in the object. So part of the energy goes into the object, part of the energy comes back again. And that's all I see, frankly, logically. So anyway, he's arguing that it's kinetic energy. So I'm just saying that, the simple, I've pointed this out, it's a simple experiment. You put a weight on the spring and it compresses an amount. And then I double the weight and it compresses twice as much. Okay, so there's no doubt about what's happening here in the sense that the first weight I lift compresses the spring an amount, and I'm going to get twice as much compression, which they say is 4 times the energy, when I do the same action. I do the same exact work. So I'm just doubling what's on there. So I take a 1 mass and put it on. It's a certain amount of work, and then when I put, and that's only 1 kinetic energy. There's only 1 KE here, and now there's 4x KE over here. And I did the same exact thing. I just add a second weight. How can the same exact work create 3 times the energy? I mean, So this is an argument. These are my counter arguments that he constantly refuses to acknowledge the existence of and reply to. How can twice the compression of the spring be 4 times the kinetic energy when it doesn't take 4 times the work to compress it? It only takes 2 times the work. Alright. So that's the background for this. I'm just saying there's good reason to say there's a problem somewhere. And he's just arrogantly saying, I've proven it, it's been demonstrated, we've proven it, blah, blah, blah. We don't have to do anything more. We've answered all the questions. When, no, you haven't answered any of them. Alright. So now it's just doing the experiment again. The same experiment he's already done. Okay, so twice I think now. But he always does the same one. Like I said, he never does it in any new way, okay, to see if it really works. So push it, okay, push the weight comparison. Instead of 1 to 2, try 1 to 4 or 1 to 5 and see if you can create that twice as much momentum effect. All right. But he hasn't done that yet.
If everything is moving in the positive direction, then the textbook model and the alternative model actually give the same prediction.
So we can't see anything in here, right? Unfortunately. I think this pink stuff is the velocity numbers. That's what it used to be. I can't read it, unfortunately. I don't know if I'll help if I do that. It says KE total, no, and it's G total. So we don't have the actual velocity recorded somewhere. And these two charts aren't even to scale. I mean, this one's a much different scale than this chart is. So I don't know what value this exactly has. I just want to know the velocity. What does your detector say the velocity is? Can I see that number somewhere? Please. All right. Put it back.
So for both of these cases, we get 0.171 for our final momenta, and we note that, well, 0.172 and 0.171, those are really close to each other. We know there is a little bit of friction on the track, so it's not quite isolated from the environment entirely, but this is a very...
So I have sped it up a little. This is all, like I said, we've all heard it, been here, done this, so a lot of it's just the same old crap.
Very good agreement, and both the textbook model and the alternative model in this case agree. So hopefully that puts to rest fears that these sensors are just giving nonsense answers.
No, it doesn't put any such thing to rest. It's still suspect.
Because then both models are giving nonsense answers, and that would be quite a coincidence.
No, it's no coincidence, because in this case you're not subtracting anything, but whatever.
So I'm going to start changing some of the masses around. So right now, this was the higher mass cart, and this was the lower mass cart. I'm going to add some masses to cart 2. I'm going to leave the mass...
It'd be nice if he would have done this in some organized way, like double the mass, triple the mass, quadruple the mass, but instead he's picked not even numbers, not whole increments of increase in the mass. It makes the math so much easier if he just goes with 2 to 1, 3 to 1, 4 to 1, or 5 to 1.
To cart 1 the same, but hopefully they should be around the same mass now. So let's actually see what this mass is. I'm going to move my camera, and once I put this on here, if it doesn't roll off. So 0.557 grams, so 1 gram shy of the other cart. So let me update these numbers for our next trial. So cart 1 is the same, cart 2 is 0.557. They're almost the same mass, and I'm also going to update that in Logger Pro. Okay.
All right, well, I didn't
Just the lower
hear
mass
the
cart.
mass.
I'm going to add some masses to cart 2. I'm going to leave the mass of cart 1 the same, but hopefully they should be around the same mass now. So let's actually see what this mass is. I'm going to move my camera, and once I put this on here, if it doesn't roll off. So 0.557 grams, so 1 gram shy of the other cart.
All right, so the other one's 1 gram shy, you said. So the other cart is 5.5, so it's 5.7. All right. So he's going to crash equal masses into each other? Cool. So both theories will agree again.
So let me update these numbers for our next trial. So cart 1 is the same, cart 2 is 0.557. They're almost the same mass. And I'm also going to update that.
So this is a Newton's cradle experiment. I don't understand how he could possibly say he's going to get a different answer here. He can't get a reflection. It's a Newton's cradle.
In Logger Pro. Okay. So again, that last case, everything was moving in the same positive direction, so we can't distinguish which model is correct or incorrect because they're both making the same predictions. They both matched up in that case. So let's try another case, and we're going to start collecting and give it a throw.
All right, so where could we disagree on this one? I don't see any possibility of a disagreement. I don't see any. What's the theory? That you made more kinetic energy? No, yeah, you didn't make more kinetic energy. You didn't make more momentum. All right, I don't remember this part, frankly.
Okay, so let's scale this so we can actually see everything that's happening here. This one, the masses were almost the same, so we get a really...
I don't know why there's two charts. I just don't get the point of this second chart. So this is the velocity of the first cart. This is the velocity of the second cart, and it has this stupid hump in it again. These are, frankly, this looks like it's just an average velocity. It doesn't really decline. This one doesn't decline. Doesn't make much sense, but go ahead. Let's just say you have really frictionless carts or something like that. Okay.
Clear instance of conservation of momentum in both these cases. Let's look just before the collision. So just before the collision, basically object 1 is the only thing that has momentum, 0.211 kilograms meters per second. And both of those models would agree with that total initial momentum. Looks like object 2 had just started to move, so that's 0.212. Both of those models would agree. After the collision, let's look at those two objects. Well, after the collision, looks like we get 0.206. And again, since they're both moving in the positive direction, and momentum 1 is basically 0, those would pretty much agree with each other, at least within the noise. Okay. So again, we have a case where there were no objects that were significantly moving in the negative direction. We had good tracking on both carts, and since nothing was moving in the negative direction, we don't have a distinguishing feature between the textbook model and this alternative.
Right, and according to him, Newton says it's possible that the cart could actually give the other cart 11. So you say it has 10 momentums, it somehow could give it 11 or 12 or 15. It just chose not to. Okay, I don't think that's what Newton's saying. But anyway, let's play along.
Model. But let's say I add a little bit more mass to this second cart. So I'm going to add more mass to this second cart. Okay. So what are we going to get for this mass in this case? Well, let's take another look. So that looks like 806 grams. So
right, so it's not a significant increase. So it's 0.86. All right. So it's only a third heavier. So it's not even twice as heavy. So it's way short of being twice as heavy. Way short. And we would expect some reflection now. Now the cart is heavier, the other cart is lighter. It's going to bang into it. It's going to reflect because it can't get all of the energy into the bigger object.
Just about 806 grams. So that is cart number 2. Let's fill in that data. Cart 1 is still staying the same. Cart 2 is, I forgot the number, just want to make sure I'm not messing that up. 806, all right.
806, he said. Okay, so it's not 86, so it's even lighter. So it's barely 20% heavier. So at that difference, you're talking like, 1/6 of the energy. You're talking about a small increase in the momentum by their theory.
806. We're going to update that on here as well.
So as stated before, I'm really not interested in these composite, computer generated average blah 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 stuff. It'd just be nice to have the actual velocity number and specifically the velocity at impact and when it's leaving. You really want the velocity just before it hits and you want the velocity just after it leaves. That's my sense of what the ideal would be.
And now let's see what we get when we run these carts into each other. So we've
Okay, so I'll
updated that.
I'll try to, blah blah blah, do this little thing, do it in little pieces.
And
we'll see how bad the frame rate is, at least this way. So we'll see whether it's worth downloading and doing the frame rate. So it's going to have to move one. Let's see, one. I'm trying to. This is after the arrow. So there's an arrow. So that's a half, more than a half of an arrow. So look, right to here would be 1, okay, and so it's going to go 1, almost 2 lengths.
And let's start taking some more data.
So he goes back first, okay, and then he pushes it forward, okay, that's all good. And so we're ahead of the arrow a little bit, so it's a little more than 1 and almost 1 3/8, 1.5, we'll just say. Okay, pretty quick. Crashes. Leaves pretty quick. Yeah, it's going to really be hard to tell these differences. So, not much hope. Doesn't look like the frame rate is all that good either, but we'll see. I mean, I really don't want to go to the trouble, but if I have to, I will. Alright, so we have initial velocity in, we got less velocity coming out, and we got a little bit over here. So makes sense that there's less velocity, obviously, and it looks like a substantial amount of less velocity. I mean, this number looks low, so I don't know what he's using as his velocity number, okay, but frankly, this distance is pretty significant compared to this distance. The amount going that way is less of a proportion than the amount going that way.
Okay. So in this case, well, we've got an object that is now moving in the negative direction.
Right, a little bit. And we have a decline in the velocity. And a little sloppy in the reading towards the end especially, but whatever.
Cart 1, after it hit cart 2, cart 1 started moving backwards. So now is when we're going to get some differences in these two models. So let's have a look at what we get. So just before the collision.
Just before the collision. So it apparently has his mouse here. Just before the collision. Okay.
Well, there's only things moving in the positive direction. So both models would agree, if everything is moving in the positive direction, both models would agree the total initial momentum is 0.219.
Okay, see, I don't want to know the total initial momentum. I want to know the velocity number you're using. And I want the velocity numbers. I really don't want all of this, pre-configured crap. Okay. So he says the total momentum line stays flat, but that's calculated based on his subtractions, I guess. I don't know. And somehow this blue line is now higher than the red line, which I don't really understand how that could have happened. Why is the blue line higher than the red line now? I don't know. I can't, I don't know. Why is that? Doesn't look quite right. I got to tell you the truth.
Again, for both of those models. After the collision, we can again look at what those velocities are and what those momentas are. Now, in the textbook model, momentum 1, we treat that as a negative momentum. So when we're adding these momentas up, I'm going to add up negative 0.036 plus positive 0.258.
So he has these final momentum numbers based on whatever he's chosen as velocity numbers. So I don't get to see where he picked the velocity. So he has it built into the system somehow, and I don't think it's picking right before the collision and right after the collision. I think it's picking an average velocity. The average velocity is going to have all this crap in it, by the way. So it's a little dangerous, frankly.
And I get from that point, I guess there's some rounding in here for the computer's model. I get around 0.221 or 0.222. But what would the alternative model give? Because again, that alternative model claims that momentum does not care about direction. When we are adding up momentas, we're always adding up positive values.
Yeah, the claim is that if I throw a ball against a surface and the surface moves, I'm not going to get back very much energy because it went into the wall. And that's all that can really happen. The object can just give its momentum to the other object, just like in the first experiment where the two equal masses hit each other. All that can happen is it can just give what it has. It can't give 11. If it only has 10, it can only give 10. That's all it can give. There's no more else anywhere else to give. And the fact is the more the wall yields, the less I'm going to get as a reflection. And the more it doesn't yield, the more I'm going to get. And the reflection is just going to be 100 when it doesn't yield at all. That's the simple argument, the simple counter argument.
So in this case, we would have to add positive 0.036 to positive 0.258. And I get from that 0.294. So 0.294. When I combine those...
Alright, so I can't see anything here. Can't really see how he's done any of this calculation. Can't see it anyplace. Can't really understand, so I have to write down every number he gives and then figure out how big a difference there is. Oh, okay. No, I'm not doing that.
Momentas as described in this alternative model. That does not give conservation of momentum.
So it's 294, and it should have been what? Yeah, I have to remember. Oh, okay. Sorry. What was the initial momentum? 208? 206? No, that isn't the initial momentum. Who knows?
The textbook model, well, within the noise, those two momentas before and after the collision, those...
Okay, so this is before and after. So he's highlighting this 222 number, and 214 is the initial he's claiming. And I don't know what these numbers are here. I assume those are the velocity numbers, but I can't really read it. So, yeah, velocity of what? The average velocity or the real velocity? It's hard to say what this is, this peak here, and whether that's included in the velocity data. the number. I don't know. Again, he doesn't explain any of this. I mean, how often does this sensor detect velocity changes? Nothing.
Match up quite well. The alternative model, not looking so good. Let's try another. I'm actually going to remove some of the mass from
I don't know why he's, just, sorry, this is just so, like, I wouldn't do it this way. So now he's just going to remove some of the mass from one of the carts, and what he should be doing is piling it on the other cart to try to make the big difference between the masses of the carts. Make the difference as big as you can and see what happens.
From this one so we can exaggerate this effect, this reflecting back effect. So I'm going to remove these two masses. Now we're changing the mass of cart 1. And let's measure this new mass. I'm going to tear that. We're going to get a new mass for cart 1. Okay. So now this is 309 grams.
309. So that's a lot better because now you have 39 to 80, which is really, close. It's 309. Okay, 30 to 80. Well, 31 to 80. So it's a little closer to a 2 to 1, but not quite there yet. I mean, 2 to 1 gives us the 133 number. That's the classic Lewin experiment with the clay on it.
Grams for cart 1. Cart 2, we're going to leave that one the same. So cart 1 is 0.309. Cart 2 is still the 0.806. And let's look at what happens when we collide these together. I need to change my mass term in this one as well. 309, just making sure that actually was 309, that I didn't get anything off there. 309, awesome. Okay, well.
Let's do it again.
Let's give this another throw.
It's definitely slower, but yeah, how much slower? All right, so, wow, so the return says this much. It looks pretty slow, frankly, but whatever. And there's clearly a big decrease in the amount of velocity in the second cart, if we take these numbers to be velocity. I mean, I can't say for sure this chart is actually saying that's the velocity at that location. And so they hit each other. The velocity inverts in this amount of time. Now he's saying that there's no exchange of momentum. And so he's saying because his black line is straight across there, that somehow it's measuring something real. When I would argue, well, it's obviously not seeing this huge change in the velocity. How the hell could the momentum remain the same when the two objects were obviously churning around? They had to both stop. So no sale, thank you. Anyway, all right, so that's all I can say is right. Okay, it looks like the line is a little below half the speed. This is obviously, 20% at least still of the initial velocity, which seems way high. So it's going backward substantially faster than I would expect it to.
Okay, again, our velocity data looks really clean. We're not getting, except at the very end, we're not getting any of these noisy spikes. We seem to...
It does have spikes in it, so it's just not play around. It's not exactly that accurate.
Be getting reliable data. But let's look at what we're finding.
So at least these charts are still not matching. So I don't know what use this one is because it doesn't have the same scale. This is 1, 2, 3. This is 1, 3, 5. I mean, I don't know. Whatever.
From this reliable data. So, just before the collision, well, we've only got object 1 moving in the positive direction, so both models would agree that this initial momentum is around 0.119.
119. So both models agree. I don't know if they both agree, but whatever. Fine. I mean, I don't know if I agree that that's what the momentum number is for the cart going in, but whatever. I don't see how you calculate the number. I don't see the actual velocity numbers.
Kilograms meters per second. They both agree on that initial momentum. Okay.
I still can't figure out why does this second chart show the red line lower. I just don't get that. I mean, why is this line lower than the blue line? It's clearly above the blue line. So why is it lower in this chart? Yeah, no, thank you.
Afterwards, well, here's where we have another one of our differences, because, again, the textbook model says if this object reflects backwards, we treat that as a negative momentum. Momentum of object 1 is negative 0.05 kilograms meters per second. Object 2 has a momentum of 0.169 kilograms meters per second. So if we add those up, we get 0.11.
So again, he's just rattling off those numbers without the velocity numbers, but fine, whatever. So he's saying the second, well, I can't read that, so whatever. He's saying this number is something like, this is supposed to be the 133, okay, so this is supposed to be 33% more momentum. Now, it's not really 2 to 1, so it's more like 1 to 2.5. So it's even a little better than 2 to 1. So it should be more than 33% going forward in terms of beyond what half would be.
9. Momentum is conserved in the textbook model. In this alternative model, again, their claim is that momentum does not care about direction. So we have to add positive 0.05 plus positive 0.169. And I get positive 2.19.
2.19. And the number was 199 or something. Yeah, I don't know if that's correct or not. I don't know, because he's not using the actual percentage number, so he's not really telling us, how much, what percentage went forward.
Sorry, positive 0.219. Those
219, okay. So that's 19. 2 plus, so that's 20. That's 20% difference. It's pretty big.
do not match. We do not get conservation of momenta with this alternative model. It does not seem to work. But we can...
That's all this is about, right? Is seams, right? So again, I can just do the Newton's cradle thing. So should I just play the Newton's cradle video over and over and over again and say, there's no extra momentum going forward. There's no extra momentum. I didn't create extra kinetic energy and then the kinetic energy disappeared and then I created it again and then it disappeared again. None of that happened. Should I just make a video of, an animation of a pendulum swinging into a wall and it keeps reflecting with, almost 99% of the energy comes back, but two momentums went into the wall and I just keep going two. I keep banging into the wall and making extra free momentum. I mean, why don't they cut down trees this way? Why don't they knock down buildings this way? If that's how the reality works, that you can double your momentum or triple it or quadruple it or do anything you want, really, why wouldn't they use that?
Test this out in additional cases. So I'm going to add some masses back onto this thing. We're going to go back to our...
All right, see, now you should go the other way. Add some masses to the blue cart. Try to get as much as you can. Try to get as much free momentum as you can.
Original setup. Let's say back to this setup where mass 1 was 0.558 and mass 2 was
558. I have 5.7. So whatever. Who knows?
0.806.
So he says 558 and 806. So 558. That was the 561 and 806. All right, so we're back to 5580. Okay, so he's going to do the same experiment again. Shit.
And now, instead of using the magnetic bumpers to keep these from running into each other, I'm going to remove those. I'm going to remove those magnetic bumpers and switch that out for Velcro. So instead of bouncing off of each other, these objects are going to stick together. So,
and this is where you lose whatever, billions and billions of kilowatts of kinetic energy.
Removing those, switching with Velcro. This is going to slightly change the masses of the carts. Let's make sure that we're not changing the masses of the carts too much. So cart 1, if we look at cart 1, that is 547 grams. So a little bit less mass than we had before. So that is 0.547. Cart 2.
547. Okay, into something way short of half. Twice, I mean.
Is going to have a mass of 794.
794, so way short of the traditional, setup, which would be much better. I mean, if he crashed into a cart that weighed the same, and then they go off together, that makes a much easier calculation than having a cart that's 1.5 times heavier.
4 grams. 794 grams for cart 2.
All right, so in this process, kinetic energy will be destroyed. Big giant pile of it will disappear. So he's not going to say that, but that's what actually happens in this experiment. You start off with a bunch of kinetic energy and you're going to lose more than half of it. So in this experiment, he's going to lose more than half the kinetic energy. So he's going to talk about momentum and calculating the momentum, but he's not going to point out that the kinetic energy numbers are going to mean you lost a lot of kinetic energy. So I don't even know how he's going to do that, frankly. There's no possible way he can do that. When he combines the two, he can't conserve the momentum because there's no backward direction. So he's going to have to really cheat somewhere. He's going to have to really make a mess out of this. I mean, this is the 5-ton train connecting with another 5-ton train, except now it's connecting with a little heavier one. And then it goes off as a 10-ton, as a 12-ton in this case.
And let's change those corresponding values on here. So that is 547. This one is 79.
So this might be a great test, all right? So if he gets the same momentum out, even though nothing's going in the opposite direction, then he's basically proven there's something wrong with his data collection. Because you already know you can't do that. Can't happen. Momentum is conserved. Yeah, I'm saying I don't know how is he going to say that the momentum isn't conserved? Of course it is. The kinetic energy isn't.
94. Okay. Again, we need to be looking at cases where the objects sometimes are going in the negative direction. So I'm actually going to take these two objects and I'm going to throw them at each other.
Oh, okay. Sorry, I didn't think he was doing that. All right, so when they stick together, this is the stupid argument, right? So we know when cars crash into each other, they stick together, but they stick together by deforming, okay, by completely crushing. And all of the energy is in the crushing. There's no like, oh, all the momentum was destroyed. Didn't happen. And in this case, the same is true. When the two carts stick together, you can't destroy the momentum. So there has to be a lot of vibration. There has to be something getting hot. There has to be some place for the momentum to go. So if you're going to stop an object, the momentum has to go somewhere. So if it's going to go and then stop, it either has to be absorbed by friction, it has to be absorbed by a wall, it has to deform something, it has to go somewhere. So he's basically saying, look, it didn't go anywhere. That can't happen. So he's going to fake my number by stating that somehow when they're both bang into each other, that somehow I'm saying there's an opposite motion somewhere, when that's going to be bullshit.
And see how those objects move afterwards. Okay. So let's give this a try. We'll see if we get good data or if it's a little bit too noisy here.
So obviously, if the heavy one's thrown with the same velocity, it's going to win. All right, and both carts are going to go off in that direction. So, see, this is a straw man argument because he didn't ask me ahead of time what I would predict on this experiment, and my prediction is not going to be consistent with what he's going to distort my prediction to be.
Let's give this a try.
So he barely got any motion out of it. So what can you say? These two look pretty even in terms of velocities. Obviously, the heavier cart has more momentum, so we have to wait until he shows us the momentum line.
Okay. So let's auto scale both of these.
Auto scale, whatever. Yeah, I trust that. So I don't even understand this momentum line, frankly. So they're both a little bit below the line here. So there's a tiny bit of motion in one direction, and that's all you have after the experiment. So he's going to claim that I claim there was this much motion and it was reduced to this much motion, or some kind of crap like that. When no, head-on collisions mean the energy's now being dispersed in some other way. You obviously have almost no momentum when you're done in the carts, because the carts no longer have the energy. They're not moving anymore. They don't have the energy. So obviously it's been consumed in all of this jitter-jatter.
And notice, other than the collision where the objects are actually moving a little bit back and forth, so that's not noise, it's the actual physical motion of those two objects.
Right, the physical motion, meaning things are banging into each other over and over again, and little pieces of stuff are going, all of that's work. So every time you vibrate something, it's work. It's not free.
We can see the momentum, the momentums of both objects before and after. We can look at that collision. Let's see what actual numbers we get for this case. So let's highlight both of these values, and just before the collision, according to the...
So this would be a time for like a heat sensor or some other thing to detect the fact that you have now dispersed the energy. The energy was in the motion of the carts, and now it's in the motion of the chemicals, the plastic, the whatever it's made out of.
The textbook model, where again the objects that are moving in different directions, we have to account for the signs of those momentas, that total momentum would be negative 0.088 kilograms meters per second. The alternative model, where there is no such thing as negative momentas, we have to add those positive values, the momentum of object 1 and the momentum of object 2 as positive values. So that would be positive 0.166 plus positive 0.25.
It's silly, right? Because they're not exchanging. So it only has to do with exchanges. If they're not exchanging, those rules don't apply. You don't add if they didn't exchange anything. All right? All they did was both lose momentum. So there's a gigantic loss of momentum. I mean, how could you subtract 300 from 1? You can't do it. You don't have anything left.
Like 3. So that gives me 0.419 for the total initial momentum of this system. What about after the collision? Again, it looks like we have some...
All right, so we could do the same exact experiment, right, out of crushable cars, where you could actually see the stuff crush. So we could have put something crushable instead of Velcro. Could have put something, you could have just made the front of the cars crushable. And then you could have just watched the stuff crush and the cars stop. So he just chose to make it less visible. But we know that's where the energy went.
We have good tracking of both of the carts. They're both moving with the same velocity. Once that kind of vibrational motion settles down a little bit, they've got the same motion. So let's look at what happens in this case. According to the textbook model, well, if we look just after the collision, so right after the collision, as close after as we can get, that total momentum adds up to negative 0.089, right beside the total momentum that we started with. But in the alternative model, again,
right beside the total momentum you started with. So obviously one of them has more momentum to start with. So you have, frankly, more momentum coming from one side than the other. And all you did was keep a little bit of that forward momentum, because one object is bigger than the other. So again, we can go back to a Newton's cradle, and I can make the point that if you let's do this experiment in a Newton's cradle, and you smash the two things into each other, okay, one with twice the kinetic energy, one, but they both have the same momentum. So a half mass object, a full mass object, you crash them into each other, it doesn't move anywhere. It stays right here in the middle. So even though one has twice as much kinetic energy, it doesn't win the collision. So again, I can counter these experiments with other experiments that don't indicate that this data, okay, is accurately representing reality.
Alternative model claims that the direction of momentum doesn't matter. So we'd have to treat these both as positive values. And if we treat those both as positive values, so 0.035 plus 0.055, we get 0.09. 0.09.
So it'd be idiotic to take the total momentum, which is this way plus that way, and say somehow it's going to equal the total momentum after, because it's almost nothing. because you've destroyed the momentum. You've destroyed the motion momentum and turned it into heat and deformation and vibrations and all of that crap. You've turned it into a crushing you can't see. But you could have just put a wad of paper in front of those two carts and done the same experiment. Just watch the wads of paper crush.
9 kilograms meters per second. In the alternative model, the initial momentum and the final momentum do not match up. So all of these have been examples of how if the object is moving in the opposite direction, this alternative model of momentum, where the momentum doesn't care about direction, it fails to match the data. But there's another way that we can test this out.
So I'm just saying this last experiment was just crap. So yeah, I'm saying, okay, there's a real experiment with this 2/3, 1/3, blah, blah, blah. I'm saying let's do it all the way. Let's get the 2. Okay, the maximum you say you can glean out of something is twice the momentum. I can hit something and give it twice the momentum I started with. That's your theory. So let's see that experiment. Let's see you double the momentum. Instead of this crap where you pervert the very concept by saying this total momentum of 2 bullets going this way and that way, and I tied a string between them, and it stopped the bullets from going, and therefore the total momentum of the bullets is 0. And that's not my argument.
So instead of having these things hit and stick together, I'm going to use the spring on here to have these objects spring off of each other. So if you look underneath there, you can see that right in there, there's a spring. So when this object hits, it's going to partially compress that spring, and then that spring is going to push back.
Yeah, it's nice and rickety. Yeah, it's very impressive. There's a little collar here. I'm not sure exactly what purpose it serves, and what the locking device is. It has a locking device on it, by the way.
And cause them to bounce off of each other somewhat.
Okay.
So let's see what happens in this case. So again, I'm going to throw these carts at each other. They're going to bounce off of each other instead of sticking together this time. And let's see what happens in this particular case.
So it's the same experiment. Now the mass is only, it's 300 more from 500. So it's not even close to the 2-to-1 thing. So again, we're talking about a tiny amount of difference here.
So again, I'm going to throw these two objects at each other.
It's not tiny. Obviously they're not close to the same mass, so there's going to be a little bit of a reflection because the other cart's going to absorb the energy, no doubt about that. But it's not going to make free momentum. So he's throwing the heavy one at the light one. So he's reversing the experiment. All right. So he's throwing the heavy cart into the light cart, which will mean the light cart. Well, let's wait and see.
And let's see what we get.
Oh, he's throwing both of them into each other again. So yes, the total momentum would be the total amount that went in, and you're going to get the total momentum back out again. So I don't know how he gets out of this one. So this ought to be interesting. You have to get the same momentum in as out. So I don't know how is he going to do this? How is he going to make the two numbers in any way different? It has to be the same amount of momentum total. So he's saying they went in with this much momentum. Now they're just reversing who has the energy. So the lighter cart, reverse direction, going a little slower than it initially was going. And the heavier cart, the lighter cart is blue? Must be. Because the lighter cart is going to absorb. I have to figure out which cart is which cart. So the heavy cart is the blue cart. The blue cart is presumably the blue line. Okay. So the blue line is going in the opposite direction. It hits and it loses momentum in terms of its reflection is slower, bounces back slower. And the red cart, it looks like it bounces back slower too. So it doesn't make any sense. One of them has to go back with more velocity. They both can't lose velocity, so there's something wrong there.
So I think we lost track.
Oh, okay, so yeah, he's conceding there's something. I forgot about that. Yes, he's saying, yeah, this is fucked up. Okay, let's do it again.
The tracking was not quite even on both of them, not quite lined up at the same time, because notice this one seems to hit a little bit before this one. All of the other cases, the timings were matched up, so I'm going to try this one again. So let's, again, we have some evidence of noise in the data that these times were.
It's not just noise in the data, right? I mean, that's a pretty big tracking error that it didn't realize they hit at the same time. That's bigger the error than you're saying it is. That's a different kind of error.
Weren't quite matched up, but let's give this another try. So, and 3, 2, 1.
All right, so I don't care about that second chart. So they hit, and now we should see. We don't see the reflection yet. All right, there it is. All right, so that's more like it. This one's slower, this one's faster. Okay, so that makes sense now. So that's exactly what I would predict, blah, 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 blah.
There, that one seems to match up much better. So let's zoom in on this data. And let's look at what's happening. So before the collision, how would we measure these momentums? Well, we still have our 0.547. We didn't change anything with the masses. All that we changed was we were using this spring to launch the objects off of each other instead of using the Velcro to make them stick together or the magnets to have them spring off of each other. In our textbook model for momentum, oh, sorry, I moved off that point. Go right there. In our textbook model of momentum, the total initial momentum is negative 0.099 kilograms meters per second. But again, in this alternative model, we can't have negative momentum, so we'd have to add these up as positive values. So we'd add 0.169 plus 0.268. And I got 0.437 for that. After the collision. So after the collision, if we look at the standard textbook model of this, our total momentum ends up being negative 0.094.
Negative 0.094 for total momentum? What are you talking about?
Again, in good agreement with our initial momentum, even though we have different ways of having these things.
I don't even understand what he did there because, frankly, yeah, 400 compared to 0.0 whatever. No chance.
Run into each other. In all of these cases, momentum is conserved when there are only internal forces acting on that system, only forces between those two objects.
There's no such thing, right? So again, he's making these arguments, and then he'll say a fulcrum is an external object. Well, the ground is an external object. So again, more mush.
And it can be any kind of force. We've used magnets to have these objects bounce off of each other. We've used Velcro to have these objects hit and stick together. That's still just an internal force between objects inside of this system. Now we're using this spring. There might be some friction on the spring, but that would still be, even if there were friction on the spring, that would still be internal to our system. So momentum would still be conserved no matter what interaction force is acting between these two objects, as long as they are only forces just acting between these two objects. I'm not pushing on another one. The track is level, so we don't have gravity, a part of gravity acting on one and not the other. Momentum is conserved in...
Well, you do have differences. I mean, frankly, the heavier cart is going to be hurt by friction more than the lighter cart. I mean, that's to your advantage, but it is a fact. Oh, brother.
The Newtonian classic physics model, momentum is conserved whenever there are only internal forces acting on the system. But going back to the alternative model, what would the momentum be after this?
I mean, duh. What one of these experiments are we talking about external forces? So again, this is just such a bullshit qualification. Nobody's talking about blowing on it or something. So what the fuck are you talking about?
Collision. Well, there's no negative momentum, so we'd have to add up positive 0.199 plus positive 0.105, and I get 0.304 when I do that. Once again, in this alternative model, whenever we have...
So whatever the number is supposed to be, so 304 isn't 437, and it isn't whatever. I can't read any of these numbers, so it doesn't really do me any good to waste my time.
Any object going in the negative direction, this alternative model fails to accurately describe what's happening to this system. This claim that momentum does not care about direction, that doesn't hold up when we're...
And again, I'll just show the Newton's cradle, okay? So I'll just, I've got a nice little slow motion clip of it, and you can explain how it makes perfect sense to you that you hit the big object with the small object, you increase the momentum in the system. So you go from having 100 momentums to having 300 momentums, and then you automatically, all of a sudden, end up back with 100 again. Okay, go ahead and live with that. I'm going to say, no, it doesn't work that way.
Doing actual experiments. Okay. But there's another thing that we can note about this, because during that collision, for part of that collision, this spring was compressed. And
this part, he really goes off the rails, frankly. I mean, this is way off a reasonable statement. Because he knows if I used a slow motion camera, I can watch the carts lose their momentum. So I can watch it happening.
We were lucky enough to get good tracking throughout that entire collision when that spring was partially.
So he says there was good tracking, and he, again, he hasn't even told me where is he measuring this velocity number from. Where? What location is the velocity detected at? Where? What period? What length? What hunk are you averaging the velocity out of?
Compressed, and when that spring was now letting go. But during that entire motion, notice that at every single point in there, the total momentum was staying the same. That black line for total momentum was staying the same. Even when
it's not sampling often enough to detect the spring's compression. It happens so quickly. It's this little tiny amount of time of the whole experiment is the actual reversal of direction. It takes a tiny amount of time, and it doesn't include it because it's making an average out of a much bigger space. So it didn't average it in because it can't see that detail.
The spring was compressed. When we were looking at the momentums of the two carts, their total momentum was staying the same. Momentum is...
That's just nonsense. So, I mean, what's the point of even having a conversation? We know momentum is mass and velocity. We know their velocities decelerates. It loses its velocity incrementally. It doesn't lose it instantaneously. It slowly loses its velocity. The other cart slowly loses its velocity until both velocities are zero, and then they both accelerate. So it's just idiotic to say the momentum stayed the same. It's just fucking bullshit.
Not being...
It's obvious the momentum is stored in the spring. I mean, it's obvious the energy is stored in the spring, okay? Whether it's energy, whether it's KE or whether it's momentum, it's obviously stored in the spring. It can't be stored anywhere else. So what's the point of this? And again, their argument is if I bang this against just one card against the wall, I'll compress the spring this much. And if I bang the other card, I'll compress it the same amount. And somehow if I bang the two cards into each other, I won't get double the compression.
Stored in this spring. If the spring was storing momentum, we would expect that when the spring is partway through its compression during this collision, we would expect to see a change in that momentum, and then, well, that momentum would be returned back to the system when the spring went back to its relaxed state. But that...
So again, I'd probably go back to, I did make a ballistic pendulum. I can go back to doing that again and try to make it more perfect. And make this free energy. This free momentum, but you can't do it. It's just no fun to do an experiment where I already know it ain't going to happen. Because if it did happen, we'd be using it. Jackhammers, all kinds of tools would be taking advantage of this fact that you can go in with 100 momentum and you can have something come out with 200. Everything would be taking advantage of a thing that doubles the momentum. Momentum really does push things over. Momentum is real pounds. It's real weight. It's real something. And they're basically trying to say it's nothing. That twice the momentum somehow isn't twice the energy.
That's not what we see. Springs do not store momentum in the way that this alternative model...
So, whatever. It's just silly. Whatever energy is, that's what they're storing. They're storing the stuff that made the carts move in, and they're going to store it, and then they're going to release it again. You're going to get back what you put in. It's clearly storing the momentum by any kind of rational means. You just said the momentum is perfectly conserved. So how the fuck can you not say that the momentum was put into the spring? It was obviously put into the spring if it was conserved. Two things came in going opposite directions, two things left going in opposite directions. How more obvious can you get?
Predicts. Let's do one more case of this just to verify. I'm going to just push one cart at the other, and we're going to see how, again, that total momentum, even during the collision, even when this spring is being partially compressed, that total momentum is still staying the same. So let's do one more example of this. Here we go.
So again, it's a tiny difference instead of the full difference. He should be using a weight that's twice as much at least. So we're talking about a 10% increase in the momentum in the direction. So the blue card's going to leave 10% faster than, it's the wrong way to say it. It's going to leave slower, but it's going to have 10% more momentum. So there it is, free momentum. You saw it.
So if we zoom in on that.
So obviously it went away less speed. The reflection is absolutely tiny this time. So I don't know how he's going to figure this one to his advantage. So the heavier cart is substantially slower, and the reflection is almost unmeasurable. So I don't know how he's going to pervert this to his side.
And let's specifically zoom in on this part here. Okay. Again, during that collision.
I don't know. It's not a very good zoom, frankly. It's just made it narrower. You just lengthened it. So his argument, he just wants to do this argument, that this stupid line up here is a real measure of something. That this isn't a preposterous averaging. It's just averaging over a big block of distance. This is not a real moment-to-moment definition of momentum, because clearly both objects are going to be losing their momentum. He's saying by my model, so he should at least, this black line is his model. The black line isn't my model. My model says both objects stop.
When the system is partially compressed, we're not getting this drop in momentum because the spring does not store momentum. However, if we were to look at the
bullshit
kinetic energy of the system.
Why don't you just do the momentum numbers?
So let's highlight that exact same section. Zoom in on that. And look at what's happening.
Good, yes. Just I mean, the point is the amount down here. I mean, what is this? This looks awful like you've now changed it again. So again, the red line is below the blue line, which I don't understand. So he's claiming the blue line has this tiny bit of extra momentum, and the red one has this tiny bit of extra. Okay, I guess that's what he's claiming.
To the energy of the system. So let me set this to 0, that part to 0. Let's set this part to, let's say, 0.1. Okay. This is a measure of how much kinetic energy the system is storing. Okay. The system has.
The system has a certain amount of capacity to move stuff, and that's it. Okay, there's nothing else. So I don't even, it's just nonsense to make this distinction. And again, I can prove it wrong just by pointing out I can lift a weight. The weight compresses a spring. I lift a second weight, it goes from having 1 kE of pressure on the spring to 4 kE. And I did exactly the same thing. How can the same exact action create a 3-fold increase in the energy? It's illogical.
So before the collision, we've got some kinetic energy. After the collision, we still have most of the kinetic energy. Again, there's a little bit of friction on that spring that's going to remove some of the energy from the system. But during that collision, we get this significant drop in the total kinetic energy of the carts. When that spring is compressed, it's not storing momentum, it is storing energy. So again, this alternative model makes the claim that springs store momentum. This data...
It showed you that by basically consistently throwing out the same stuff that went in. So you're saying it threw out more momentum. Okay, I'm saying, of course, it didn't. But anyway, continue.
Shows that they don't. It's not momentum being stored, it's energy being stored. When the spring compresses, some of that kinetic energy is being converted to spring potential energy, and when the spring launches those objects again, it gives, again, most of that energy back to the system.
So again, I don't, this whole idea of processing all the data ahead of time, I'm not interested in. I just want to know real velocity numbers, and then we can test those by frame rate.
So,
but I am really not interested. Frankly, been here and done this so many times. So again, fine. You did an experiment. You claim it's valid. Fine. I'll just keep showing the alternative argument, which is, why doesn't it work in a Newton's cradle?
Overall, what does this tell us about how we can compare models? First, if I want to compare these models to figure out which one is viable, I need to find conditions where these two models, or any two models, make different predictions for the outcome of an experiment.
Right. So look, the simple principle is, if one of them doesn't conserve, then it's not real. So you're saying you don't have to conserve momentum. You can make extra motion in the universe. All right, I'm saying you can't, okay? And I can show the experiments where you lose half the kinetic energy in a magical way without using any momentum. So they convert from a 5-ton train going 10 miles an hour into a 10-ton train going 5 miles an hour, and claim that magically I lost half the energy, but I didn't lose any momentum. So somehow I used up the kinetic energy, but it wasn't in the form of momentum when I did it. Which is nonsense, frankly.
And then we have to actually do that experiment and see which of our models matches with the data. In this case, all of our cases, no matter what kinds of objects that we had running into each other, whether we used the magnets to have the objects interact.
Oh, you didn't bang it against a brick wall, did you? No. Simple enough experiment. And then you can explain how the brick wall has twice the energy in it.
We had Velcro having the objects stick together, whether we had this spring as the force that's acting on the two objects. As long as the forces in this system are all internal and there's no external forces, momentum is conserved. Direction matters in this conservation of momentum, so if I've got an object moving in the positive direction, we're going to call that a positive momentum. If I've got an object moving in the negative...
Right, then I have negative, right. So if I shoot a bullet out of a zip gun going that way and one going that way, I have zero momentum. Yay! So I had an explosion. There's things moving, but there's no momentum. Yeah, bullshit.
Direction, we're going to call that a negative momentum. All of those predictions matched with the data to a high level of accuracy. Like, again, we were never more than a few % off of keeping all of that momentum just before and just after the collision. On the other hand, considering this alternative model, when everything was going in the same direction and we didn't have to worry about that objects going in the negative direction, it did match up. But as soon as an object...
Yeah, it didn't match up because I don't know how you're detecting the velocity. We want the velocity at impact. We want the velocity that this leaves with. Initial velocity. Did you put those actual velocities into your calculator? I don't think you did.
Object was moving in the opposite direction. This model of momentum failed. It did not give conservation of momentum like the proponents of this model seem to think it should. We also found that if we use a spring for this collision, during the collision itself, the total momentum is staying the same. The spring does not store momentum. What it does store is kinetic energy.
Look, the Newton's cradle is the better example, I'm just saying, because you don't have to worry about a spring, right? It's a perfectly elastic experiment. The steel ball. There's no losses. There's no deformation permanent. There's none of that crap. So just bang your one mass into your 4 mass and show me that you can create 4 times the momentum. I mean, twice the momentum.
So, again, I hope this is a clear way of delineating between testing the predictions of two competing models and using the data to determine which of those models is actually viable.
Right. Now, he could have done the experiment. Just put a brick on top of this cart. So it barely moves. It's supposed to move with twice the momentum. So you put 100 momentums in, you get 200 momentums out. And that makes sense to you people. So if I put a second, a third cart, and a fourth cart, and a fifth cart, right, just put more bricks on them, I can make more and more momentum.
And I hope I've demonstrated that this alternative model is not viable.
Whatever, we'll see. Okay. Time will tell. Okay, none of these experiments have been done. 300 years of this silly theory. They haven't proven any of it. Okay, they have these little chicanery experiments, right? Back in the 1700s, it was dropping round things into clay. They didn't talk about dropping cylinders into clay. No, had to be a round thing. So it's always these little conditions they have to do these experiments in. So they won't show us to taking 4 times the fuel to go twice as fast, or 9 times the fuel to go 3 times as fast. You want to go 3 times faster, right? You're going 20 miles an hour. You want to go up to 60 miles an hour, 9 times the fuel. Who believes that? But these people. Yeah, but everybody. Everybody believes that. Okay, I don't believe it.
Classical physics.
I mean, it gets worse and worse, right? I mean, I'm going 20 miles an hour. I'm going to go 80 miles an hour. 16 times more fuel.
Isaac Newton's model of momentum, the kind that is taught in every reputable physics class, that one is supported by the data. All of this data that we took supports that model. So that's it for this session. Again, I hope this was interesting. If you have questions, please throw those into the comments. I'm sure I'm going to get some comments back about this one. But again, be respectful when you're talking or responding, when you're posting or responding to any comments. And I'll see you in the next video.
Whatever. Yeah, we'll see. We will see again. So they have, this is it. This is their little dropping round things into clay experiment, this 1 to 2 thing. So they won't do the 1 to 4 thing, okay, for whatever reason. And they won't do it with plain elastic. So it always has to be a catch, a spring, or some other kind of bullshit. The carts should be able to just bang off of each other, frankly, and conserve most of the momentum. So why don't you do it that way? Why, anyway, blah, 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 blah. No point in asking why. Yeah, why haven't they repeated the Eddington experiment from space? No point in asking why. It's a nice, rational question, no rational answers. All right, so is that all I need to say? Yeah. I mean, I just could illustrate one more time. I just don't understand how these people can think twice the spring compression is 4 times the energy. I just don't know how they can think that. But whatever. Yeah, I won't bother drawing it again. All right, so that's it. I guess we'll just leave it there and see where it goes and such. So we've already been here and done this, right? We have 60 versions of this experiment. I guess I could go back and dig up the high school teacher one where it comes out my way, okay? But whatever. It's just not much point in arguing the same crappy little niche experiment when they still haven't proven it takes 4 times the fuel to go twice as fast. Okay.